Hi, and welcome to Dr. V's AP Chemistry webcast. In this webcast, we're discussing the Nernst equation. Here's what I'd like to accomplish in this webcast. First, I want to introduce the Nernst equation itself. It's a really important expression. And we're going to use the Nernst equation to relate changes in the reaction quotient to the cell potential when we're at non-standard conditions. Then we're going to go and solve a sample problem. We all use batteries every day, and from experience, we know that the voltage drops as the battery gets used. Different types of batteries discharge at different rates, but we always see this drop in the voltage. Eventually, the battery establishes equilibrium. It's got a voltage of 0 volts. This is what we mean every day when we talk about a dead battery. A dead battery is not dead, it's just established equilibrium. The diagram that I'm showing here illustrates a very typical wet cell, the Daniell cell, a zinc half cell with a copper half cell. And we've got the balanced equation. Zinc reacts with copper 2 ions to make copper metal and zinc ions. As the cell is running, the balanced equation shows us that the concentration of zinc ions in the left-hand compartment increases, and the concentration of copper ions in the right-hand compartment decreases. It's time to think about this, though, from an equilibrium perspective. We can talk about the reaction quotient, Q, which we discussed in our equilibrium unit, and Q gives the ratio of products over reactants when you're not necessarily at equilibrium. So you're looking at this ratio. And of course, we don't include solids in our expression for Q. So Q for this reaction is the concentration of zinc ions divided by the concentration of copper ions. As the cell is running, the balanced equation tells us that the value of Q is going to increase. So as the cell is operating, Q is increasing and Ecell decreases. And this relationship is what the Nernst equation explores in more detail. It was developed by Nernst, who was a German physical chemist, who won the Nobel Prize in 1920 for his work on electrochemistry. He developed a mathematical equation so that we can calculate Ecell at non-standard conditions. So if our concentrations aren't 1 molar, if our temperature for the cell is not 25 degrees Celsius, we can calculate the cell voltage. Here's the Nernst equation in all its glory. Ecell, our non-standard cell voltage, equals E0 of the cell minus RT over NF times the ln of Q. There are a lot of variables here. Let's go through them one by one. E0 of the cell is the standard cell potential. When you calculate the cell potential from your table of standard reduction potentials, that's E0 for the cell. R is the universal gas constant. It shows up in all kinds of places. T is the temperature. It's got to be in Kelvin. N is the number of electrons transferred in the overall reaction. So you do need to know the balanced equation to know how many electrons are lost and how many electrons are gained. And then our fancy F here is the Faraday constant. It's usually written with a fancy cursive F just to make it look cute, I guess. And that's equal to 96,500 coulombs per moles of electrons. It's a very important constant. And then, of course, we have Q, our reaction quotient. This whole equation is the Nernst equation. Now, the full form of the Nernst equation is on your AP equation sheet, but there is a simplified form that also appears. Ecell equals E0 of the cell minus 0.0592 over N times the log of Q if we're at 25 degrees Celsius. So what is going on with this equation is that R is a constant, T is 25 degrees Celsius or 298 Kelvin, the Faraday is a constant, and we've converted from the natural log to the common log and consolidated all of those constants, and that's where we get the 0.0592. And then N is still the number of electrons transferred in the equation. Sometimes this one's a little bit easier to work with. In AP Chemistry, the most important application of the Nernst equation is relating Q to Ecell. So we've got the Nernst equation here, and let's talk about how Q fits in. If Q is equal to 1, so your concentrations are 1 molar, and we're assuming the temperature is 25 degrees Celsius, well, the natural log of 1 would be 0. And so that log term and everything multiplied by it is 0. And so the voltage of the cell would be the standard cell potential. But we can also manipulate the initial concentrations of the ions in those solutions to not be 1 molar. So if we make the initial concentrations of the wet cells so that Q is less than 1, in other words, the concentration of the products is less than the concentration of the reactants in their respective half cells, the log of Q would be a number less than 0, because that's how logs work. And that means we're subtracting a negative term from the standard cell potential. So if I'm subtracting a negative term, Ecell is going to be greater than the E0 value for the cell potential. It works in the opposite direction as well. If we manipulate the initial solution concentrations so that we're starting the cell with Q greater than 1. In other words, the concentrations of the products in our balanced equation are higher in the half cells than compared to the initial concentrations of the reactants in the half cell. The natural log of Q will be a number greater than 0. And I have to subtract that log of Q term from E naught. So I'm subtracting a positive number, and that means E cell will be less than E naught if Q is greater than 1. Of course, that's how we introduced this whole idea in the first place. For AP Chemistry students, this kind of reasoning is the heart of what you're asked to do. Let's work through a problem together. We have a voltaic cell that we're going to construct using a cadmium half cell and a tin to tin 2 half cell. We need a balanced equation, and we need to determine E naught for the cell. Here's where the Nernst equation piece comes in. If the initial cadmium ion concentration is 0.50 molar, and the initial tin 2 ion concentration is 0.3 molar, will E cell be greater than, less than, or equal to the standard cell voltage? We're going to go one step further beyond the AP level and actually calculate the cell potential to back up our answer. So here's our strategy. We need to calculate the standard cell voltage, so we're going to need a standard reduction potentials table and write the balanced equation. And then we're going to use the Nernst equation to find and calculate that non-standard cell voltage. We've got a cadmium half cell, we've got a tin 2 to tin half cell. Let's start by finding the balanced equation and the standard cell voltage. We need a standard reduction potentials table, so I just took a screenshot of a portion of the table that has both of these half reactions in it. We've got the tin 2 half reaction, we've got the cadmium half reaction, and I see that the tin 2 half reaction has a higher standard reduction potential than the cadmium half reaction. This is really important because it helps us to figure out the correct balanced equation. Since the tin 2 half reaction has a higher E naught value, of these two half reactions, it's got the greater tendency to undergo reduction. And the cadmium half reaction has a lower E naught value, which means it has a lesser tendency to undergo reduction and a greater tendency to undergo oxidation. This means we're going to keep the tin 2 reaction as written as the reduction reaction. So we'll write that down and write down its E naught value. For the cadmium half reaction, we want to flip it around and write it as an oxidation half reaction, and that means we need to change the sign of E naught. So we'll flip the cadmium reaction, change the sign of E naught. Both half reactions involve 2 electrons, so I'm going to add up my equation, write out my balanced reaction, and I add up the 2 E naught values to get the standard cell voltage, which is 0.26 volts. And I'm making a note to myself, 2 electrons were transferred in the reaction, and I'm going to need that on my next slide. Let's go ahead and calculate the cell potential at 25 degrees Celsius for an initial cadmium ion concentration of 0.5 molar and an initial tin 2 ion concentration of 0.3 molar. We've got our balanced equation. We found that on the previous slide, and we also have the standard cell voltage of 0.26 volts for this reaction. We also know from the equations that we wrote on the previous slide that n equals 2. There are 2 electrons transferred. So now we can start thinking about it from a Nernst equation perspective. We can write an expression for Q based on the balanced equation. Since the solid metals aren't included, it's the cadmium ion concentration divided by the tin 2 ion concentration. We know both of those values. They were given to us, and we can substitute them in and get a value for Q. Clearly, Q is going to be greater than 1. And since Q is greater than 1, E cell will be smaller than the standard cell potential. This is as far as you need to go. You don't need to do the full calculation out. However, we're here. We're feeling really mathy today, and they're not very difficult problems to do. So let's finish the problem. Let's substitute in. We know E naught is 0.26 volts. We know N is equal to 2. We know Q is equal to 1.67. And at this point, all we have to do is finish evaluating this expression. We take the log of 1.67. We start putting our terms together. We end up needing to subtract 0.0066 from our standard cell voltage. And what we find in the end is that the E cell at these non-standard conditions is 0.25 volts. Now that's actually consistent with what we had predicted. We had said E cell would be smaller than the standard cell voltage, and it is. It's not a big difference, but it is smaller, and that's what we anticipated. Often we see with these Nernst equation problems that the difference in the cell voltages is pretty small. It's really important that AP Chemistry students are able to predict how E cell will change compared to E naught. Will it be larger? Will it be smaller? Would it be unaffected? But you don't have to do it using the Nernst equation. However, the quantitative reasoning provided by the Nernst equation is your safest bet when these kinds of questions come up. Do not use LeChatelier's principle to support your answer. You risk not getting credit at all. The Nernst equation has a number of important applications outside of voltaic cells. Nerve conduction is all about having a potential gradient because the concentrations of ions on opposite sides of a cell membrane are different. Another interesting application of the Nernst equation is a concentration cell. We can build galvanic cells with the same materials in both half cells, but by varying the concentrations of the ions in the two half cells, we can actually generate a voltage. For example, in this diagram, we've got a dilute nickel solution on the left, a more concentrated nickel solution on the right. We both have nickel electrodes. Since we have the same species doing the oxidation and reduction, the standard cell voltage is 0. But we can set Q up here so that Q is less than 1. And when Q is less than 1, Ecell is going to increase. And so we do get a positive cell voltage here. Eventually, the two solutions will establish an equilibrium. They'll both end up at the same concentration, and at that point, the cell voltage will be 0. These are actually pretty easy to build, and I often have my students do them in class. That's really everything I wanted to tell you about the Nernst equation. It's important to remember we can use the Nernst equation to determine how cell voltages will change at non-standard conditions. We can do it mathematically and actually calculate it out. But it's really important that you can do it conceptually, that if Q is greater than 1, Ecell will decrease compared to the standard voltage. And if Q is less than 1, Ecell will increase compared to the standard voltage. I certainly hope you found this helpful. Subscribe to my channel so you get all my latest videos, leave a comment, and study chemistry every day. That's how you get better.